us discuss notion of convergence. For a random variable, sequence of random variables. Now, whenever we talk convergence in a sequential sense, we know the sequence of real number. First of all, let us discuss the sequence of real number an. We say that this sequence of real number, so it is basically a function from this natural number to some real number. For each value of n, we are getting a real number. So then it is known as the sequence of real number. So that is denoted by an. So we say that this sequence it is a convergence sequence, and we denote that limit n goes to infinity an is equal to a if for any epsilon greater than 0 there exists a natural number n naught such that if you take the difference an minus a will be less than epsilon for all n greater than equal to n naught. So, this is the concept of convergence in sequence of real number. Now, if we consider the sequence of random variables, so in that case it is a sequence of functions. So, each n we are getting a random variable x1, x2, xn. So, this is a sequence of random variables. So, that means each n belongs to natural number, xn will be a function from sample space S to R. Now, how we will define that this is a convergence, like, because it is not a real number. So because we, and also it is not just a function, it is a random variable. So, that means it is a measurable function, but we can talk about some the probability also. So, some xn for any s belongs to s, xn is this is a real number. So, if you have to define that it is converging to some random variable x, so then how we can define this? So, there are different approach to define this convergence of the sequence of random variable. One is called the convergence in probability. So, convergence in probability. So, a sequence of random variable xn is said to converge in probability, is said to converge in probability to a random variable x. So, it may be a constant random variable also. So, we can say some a real number. So, in general converge in probability to x if for any epsilon greater than 0, if we consider the difference xns minus xs, this difference greater than epsilon, or we can take greater than equal to epsilon, and this is all s belongs to s sample space such that xns minus xs greater than equal to epsilon. So, this will be a subset of s, it is a event. If you take the probability, then this will be a real number. Now, if this n become a sequence of real number now. Now, if this goes to 0, so that means if we can write limit n goes to infinity, probability that, for simplified notation we will just write xn minus x greater than epsilon. This is same as this notation, xn minus x greater than epsilon. This is nothing but limit n goes to infinity an. So, this probability, if this goes to 0, then we say that if for any epsilon greater than 0, this if, so that we can remove this, or we can say that if limit n goes to infinity this, limit n goes to infinity this is equal to 0. So, same as actually this is the some simplified notation I wrote. So, we can say that now very simple way, this is equal to 0, then we say that xn goes to x in probability, converging in probability. So, let us discuss one example. So, this example, suppose if we consider this suppose let x1 x2 xn be independent IID random variable from, so suppose all have same random variable normal mu variance sigma square. Now, if you change, then depending upon n your random variable will, number of random variable change. So, let us consider xn bar. So, we can have this all this IID random variable, xn bar is equal to summation of xi by n, this sample mean. So, we know that expected values of xn bar, this is equal to mu, and variance of xn bar that we have already discussed earlier, or we can compute also, this is sigma square by n. So, let us compute it. So, expected values of xn bar is equal to expected values of x1 plus x2 plus xn by n. So, this is 1 by n expected values of x1 plus expected values of x2 plus expected values of xn. So, by definition, now expected values of x1 all are having same mean. So, mu, because all x are coming from same normal distribution, so all have mean mu, n mu by n, this is equal to mu. So, similarly variance of xn bar, you can find that variance of x1 plus x2 plus xn by n, but n is a constant, so it will be 1 by n square, variance of x1 plus variance of x2 plus variance of xn. So, there will be some covariance term, but it is independent, covariance will be 0. So, then all variance will be same, sigma square, this is n sigma square by n square, this is sigma square by n. So, that we know. Now, claim is that xn bar as n goes to infinity, xn bar, this is a sequence of random variable n greater than equal to 1, xn bar, so this sequence of random variable converges to this a constant random variable mu as n goes to in probability, we say converges to mu in probability. So, how we can show that? So, note that by Chebyshev inequality we know that from Chebyshev inequality. So, here you can see that we use the Chebyshev inequality. So, Chebyshev inequality we know that for any random variable, let us recall this Chebyshev inequality. So, Chebyshev inequality says that for any random variable x minus probability that absolute value x minus mu greater than equal to epsilon less than equal to sigma square by, that is the variance. Inequality for any epsilon greater than 0, probability that xn bar, this mean mu greater than equal to epsilon is less than equal to, see that variance of xn bar is sigma square by n and this is epsilon square. Now, this is probability is always greater than equal to 0 and this is goes to 0 because it is just a sequence of real number as n goes to infinity, which implies limit n goes to infinity, probability that absolute value xn bar minus mu greater than equal to epsilon is equal to 0 by Sandwich theorem. Hence, by definition you can see that if this satisfy, we say that xn bar is converges in probability to x. So, hence xn bar converges to mu in probability. So, this is one notion of convergence. So, another convergence, it is known that almost sure convergence. So, almost sure convergence is that, so it is nothing but this function converges in point wise, limit n goes to infinity, xns goes to, so let us explicitly write that. So, almost sure convergence. Let let xn be a sequence of random variable. So, random variable, a sequence of random variable, a sequence of a sequence of random variable xn is said to converge to x almost surely if, so basically it is converging for all s if probability that, so consider this all s belongs to this s, limit n goes to infinity, this is a function, so point wise it is converging for all s. Now it may not be converging, so some of the s may not be, but if this probability is equal to 0 and or it is equivalent to say that probability that all s belongs to s, limit n goes to infinity xn s is equal to xs. So if we see that this probability is 1, so then we say that xn converges to a point x almost surely. So so you can see that suppose this is a sample space and you have some set some a, so that probability of a is 0 and this sequence of random variable converging all point except suppose this point a, so then it is called the almost sure convergence. So almost sure convergence, it is like that we are taking the majority where there is some possibility or probability, so some weight is there. So if the probability is 0, we will not considering their votes. So like some kind of like in a layman we are saying that, but this is the mathematical way to defining is that if this point probability a is 0 and then if it is actually agreeing for all other point where this probability is 1, so then we say that it is a almost sure convergence. So another notion of convergence is called the convergence in law. So convergence in law or convergence in distribution also we say, convergence in law or distribution we say, convergence in distribution. So a sequence of random variable, so sequence of random variable xn is said to converge in law to a random variable x if limit n goes to infinity fn x is equal to, sorry this is x, fx for all x belongs to the real number where f is continuous. So all these x where f is continuous, if you see that fn is equal to f, here we denote, actually the notation is that here fn x is the cumulative distribution function of xn, the of the random variable xn, and fx is the cumulative distribution function of the random variable x. So this is the convergence in law. So we will discuss this some more examples also in the following some whenever we learn some of the theorems or some of the results, how it is utilized. So some of the here let us discuss first, it is called the weak law of large numbers. So weak law of large numbers it says that, so here we have already shown this kind of things, but here we assume that convergence is probability that mean and variance exist of a, and it is a normally distributed random variable, but weak law of large number is more stronger than this concept, that let x1 x2 xn be a sequence of independent identically distributed random variable with finite mean mu. For variance they did not say anything, and xn bar is the mean of these things. Then it is saying that weak law of large number says that as n goes to infinity, xn bar converges to mu in probability. So this is called the weak law of large number. So weak law of large number says that the so it is abbreviated as weak law of large number. So let x1, x2, xn be sequence of identically and independent distributed random variable, be a sequence of independent and identically distributed random variables, because they are identically distributed random variables with, so because they have same mean, xi is equal to mu for all I is equal to 1 to n. Then it says that if you consider xn bar, let xn bar is equal to x1 plus x2, this is the mean, sample mean. So let xn bar is equal to x1 plus x2 plus xn by mean. So this then converges to mu in probability, we write mean as n goes to infinity. That means for any epsilon greater than 0, probability that xn bar minus mu greater than equal to epsilon, if you take the limit n goes to infinity, this is equal to 0. So this is called the weak law of large number. So we are not going to prove this, and strong law of large number says that the same thing. So here we will not go this in details. So this is just to learn it, weak law of large number. And strong law of large number says that if x1, x2, xn be a sequence of independent identically distributed random variable is with finite mean mu, then for any epsilon greater than 0, limit n goes to infinity xn minus mu greater than epsilon. So basically this limit actually inside here. So this all is such that it is not converging actually to mu. So this is equal to 0. So that means strong law of large number says that limit whenever if you strong law of large number, actually this statement same, only SLL as the strong law of number says that the strong law of large numbers. So this is strong law of large number. So this is says that, so all these things will be same. Let x1, x2, xn be, let us write in a abbreviation or be a sequence of independent and identically distributed random variables with, because they are independent and identically distributed and their common mean xi is equal to mu for all I is equal to 1 to n. Then strong law of large number says that xn bar, which is nothing but x1 plus x2 plus xn by n, converges to mu almost surely, as n goes to infinity, this is almost sure convergence. So in other way you can say that for limit probability that limit n goes to infinity, this xn bar is equal to mu, this is equal to 1, or this is in other way you can say for any epsilon greater than 0, if you consider this probability limit n goes to infinity, there is a difference xn bar minus mu greater than epsilon, this will be is equal to 0. So that means it is not converging. So this is same as to say that limit n goes to infinity xn bar, this is not equal to mu, this is equal to 0. So, this is equivalent to say these things. So, this is actually it is here it is represented. So, this is the strong law of large number. So, we will not go through more details about it, only to mention that. So, strong law of large number, weak law. So, why it is strong and why weak? Because almost your convergence is more stronger than the convergence probability. So, there exists some of the examples where sequence of random variable converging in probability, but it may not converge in almost surely. But if a sequence of random variable converging almost surely, so then it must converge in probability also. So, that is why strong almost sure convergence is strong. So, that is why it is a strong law of large number, and for because it is a convergence in probability, so it is called a weak law of large number. So, more details we will not go through here. So, now how it is this law of large number, how it is utilized. So, there are many examples in the real life situation also. You may see if you go some of the suppose in a village, in a mela, so there are different gambling going on. So, it seems like or are like a some randomly it is happening, and somebody may be fortunate, they are getting the profit. But if you see very the theory part where it is utilized. So, law of large number, it is saying that whenever n is very large, so it is not at all random. So, it is going to a particular value. So, that value actually they are actually designing this game such a way that, so the other side, those who are playing, so that shopkeeper or somebody, those who are designing, they will always get the profit whenever it is a long run. So, long run actually what will be the average behavior, what is the average profit. So, that actually they can conclude it, they can compute it. But in a particular trial, it may be random, somebody winning we are seeing, but in a long run, so it is actually it is not random at all. It is mostly it is converging to a particular point. So, that is actually suppose you have a fair 6-sided die, each side has an equal probability of landing face up when die is rolled. Now, you roll the die 100 times and record the outcome of each die roll. What is the expected value mean of the outcome after rolling the die 100 times? So, maybe each die, whenever you are rolling each time, we do not know what value it will come. But if you roll 100 then 1000 number of times or 10,000 number of times, so you can expect that it will be this number into 1 by 6. So, that value it should occur. So, that number of times it will occur, that we can conclude. So, more details of this example we can discuss later if we get time. Then it will be very interesting that how this law of large number is useful in the gambling. So, how they are using it. So, more details it can be also discussed. So, you can find some examples. Now, we will discuss some another topic. It is very important. So, most of the time when we do not know the distribution, some data we collected and we do not know what is the distribution exactly. So, it is a Poisson distribution or binomial distribution, or it may be exponential distribution, gamma distribution, we do not know. So, then we say that let us assume it is a normal distribution. So, what is the basis, so like why we are saying that it should be a normal distribution, why it may work or not. So, that is actually some of the basis is, it is called the central limit theorem. Central limit theorem. So, central limit theorem is a fundamental result in a probability theory. It holds immense significance in various fields due to its versatile applications. The theorem exists in multiple versions, each catering to different scenarios. So, here we discuss one version. So, here this version we are discuss. Consider a sequence of independent and identically distributed random variables. So, there are many versions. So, here we consider these things. Each random variable xi has a mean denoted by mu and variance denoted by sigma square. Now, let us define this Zn. So, let us discuss that. Let x1, x2, xn be a sequence of random variable So, sequence of independent and identically distributed random variable with, so here we assume that it has finite mean because all have same mean and variance of xi is equal to sigma square for all I is equal to 1 to n, because identically distributed random variable their mean and variances are same. So, let z is equal to xn bar minus mu by sigma by root n. So, if we simplify these things, root n is equal to xn bar minus mu by sigma. So, where is xn bar? Where xn bar already we denoted, this is x1 plus x2 plus xn by n. So, we just computed that what will be the mean of expected values. Xn bar is nothing but mu, and what is the variance of xn bar? This is sigma square by n. So, what this transformation we are taking, this is we are subtracting the mean and dividing by the standard deviation of the xn bar. So, this is sigma by root n. So, then the central limit theorem says that then, so suppose, so let us because it is dependent on n, let fn so fn z be the cumulative distribution function of z, and we denote like this phi z, this is defined by minus infinity to z 1 by root 2 pi e to the power of minus t square by 2 dt. This is the let this is nothing but be the cumulative distribution function of the standard normal distribution, cumulative distribution function of normal 0 1, standard normal random variate. So, we say that of the standard normal random variable random variate. So, sometime we denote by n01. Basically, normal distribution mean 0 and variance 1, we say standard normal random variate. Then limit n goes to infinity fn z for any z, this is equal to phi z for any z belongs to the real number. In other words, we say that Zn converges to n01 in law as n goes to infinity. So, the distribution function of fn z, it looks like the distribution function of standard normal variate whenever n is very large. It is known as the central limit theorem. So, central limit theorem has many applications. So, here the central limit theorem it is given. So, you can see that. So, the purpose is to standardize sum of n random variables. The main result of C.L.T as n goes to infinity, the distribution of Zn tends to the standard normal distribution. Mathematically, limit n goes to infinity, Zn is very close to normal 0 1. So, this is the central limit theorem. So, if you graphically represent that, suppose if you take this transformation Zn, this is nothing but xn bar minus mu by sigma by root n, then so as n small, so it looks like maybe this. So, whenever n large, so now let us do this, n small, suppose n is equal to 10, so n is equal to suppose 50, now n is equal to 100. So, whenever n is very large, so it looks like, suppose it is n is equal to 1000. So, this is nothing but close to very standard normal variate. So, this is the theorem. So, whenever n is large, then this distribution or probability density function of Zn and probability distribution function of Zn will be very close to the z, which is nothing but normal 0 1. So that is because, so that's why n, whenever n is large, we consider it is a normally distributed random variable. So this is the central limit theorem. There are many applications. So some of the applications, suppose, so this is the, so cumulative distribution function of f z and z converges to the standard normal c d at phi z as n goes to infinity. This convergence is crucial for understanding the behavior of the sums of random variables. Suppose you have a population of test score with mean 50, mean of 70 and standard deviation of 10. You randomly sample 50 test scores from this population. What is the mean and standard deviation of the sampling distribution of the sample mean, and then find the probability that a sample mean is greater than 72. Let us discuss one numerical example where central limit theorem may be utilized. So here, suppose you have a population of test scores with a mean 70 and a standard deviation 10. You randomly sampled 50 test scores from this population. So basically you have sampling x1, x2, x, so how many? So here 50 test scores, n is equal to 50. So they are IID random variable from x. So with the mean, all have same mean because they are identically distributed random variable, because it is saying that population. So from the population it is drawing test score mean 70 and standard deviation sigma or sigma square, we can say variance or xi, this is equal to, so because it is standard deviation is 10, so this is 10 square, so this is 100. So for all I is equal to 1 to 50. So this is actually given. So now see that here this population, what is the distribution, it is not known. So if it is not known, it is a gamma distribution or it is a exponential distribution or normal distribution, it is known, not known, then which distribution we will use? So here it is asked that what is the mean and standard deviation of the sampling distribution of the sample mean. So that can be found, because if you find the sample mean x n bar, so here n is equal to 50, so this is nothing but x1 plus x2 plus xn by n. So then from here we have already computed, then this is expected values of xn bar will be same as this mean, this is 70, and variance of xn bar, this will be sigma square by n, sigma square by n. So sigma square is 100 here and n is 50 here, so then this is nothing but 2. So this is 2. So this variance of xn bar, it can be found, because finding variance of xn bar and expected values of xn bar and variance of xn bar, we did not use any normal distribution or any distribution. You can see here where we computed just now. So here just you can also find out that, so I think this is little before we did it, whenever we discuss this law of large number, yeah. So here we have, you can find that. So here I think, so here we can see that here no, it is any for random variable xn bar mu and variance of xn bar also you can compute if you know the, because IID random variable variance of xi is sigma square, so it is sigma square by n, that we computed. So now we can compute this value. So that is we have already found for this example. Here we can found. So expected values of xn bar is 70 and variance of xn bar is 2. Now what is the mean and standard deviation of the sampling distribution? So the standard deviation of xn bar, standard deviation of xn bar will be root over of variance of xn bar, this is root over of 2, this is root 2. So next question is that, then find the probability that the sample mean is greater than 72. So we have to find that sample mean xn bar, this is greater than 72. So this probability we have to find. So now how we can find? We don't know the distribution of xn bar. Here it is nothing given about the population, only mean and variance given. Now, if you use the central limit theorem, we know that if you consider this Zn, this is xn bar minus mu by sigma by root n, it has approximately, as n goes to infinity, normal 0 1 whenever n is large. So, we can consider here, because it is also which n it will be large, but mostly it is followed whenever n is greater than some 30 or some of the values. Most of the time we can assume that it may be, we have to check that whether it is working, but here we can assume that whenever n is large, it is a normal distribution. So, n is 50 here. So, now let us consider xn bar minus mu. So, what is mu? Xn bar minus mu is this is 70, mu is nothing but 70, that is the mu, and sigma by root n, sigma by root n is sigma square. So, variance of xn bar here, it is variance of standard deviation. So, standard deviation of xn bar is nothing but root 2. So, that we can replace here. So, which implies probability that xn bar, so now this probability can be same as xn bar minus 70 by root 2, which is greater than, if you do the same operation here, then this inequality does not change, this probability will be same. So, then this is nothing but probability that this xn bar minus 70 by root 2, this is equal to okay. So, that is why this is coming like numerically complicated, but we will find out. So, then this is this Zn, so this is Zn greater than 70 minus 2, 70, so 2 by root 2. So, this is equal to probability that Zn greater than root 2. So, now we know that Zn has normal 0 1, approximately normal 0 1 like this. So, Zn greater than root 2 is some value here, suppose 1.414, some approximate value will take, and this is the root 2 suppose, and this is minus root 2. So, then by symmetry, this area probability that Zn greater than root 2 is same as probability that Zn less than minus root 2. So, we will take a approximate values of Zn, the approximate values of root 2, this is Zn less than minus 1.414. So, now why I just used it, because we want to use this table. So, this table is given here, normal distribution table, and it is the negative value only it is given. So, this is 1.-4 and up to 2 division place it is given minus 1.4 and 1 is here. So, this is minus 1.41, this is 0.7927. So, this is approximately 0.07927. So, so you can see that this probability up to minus 1.41 is here. So, minus 41 minus 0.07927, 0.079, which is equal to 0.07927. So, this is one application that whenever n is large, or whenever we do not know the distribution, we can use any distribution, but best way that by central limit theorem, if n is large, we can use that. N is large, then this mostly it will be follow as a normal distribution. So, by assuming that it is a normal distribution in this transformation, then we can find the required probability. So, this is I think we completed the syllabus for probability theory for data science. I hope you have followed and enjoyed this course. So, you can see the reference books for more details, and you solve the assignments, and then if you solve more problems, you can clear your doubts, and then I think you have understood clearly, and that is the I think it is the end of the course. Yeah, thank you.